All right, we're going to do a few more problems from 18.2. So when we want to find a line integral, the job here is to find the line integral of this vector field, yi plus xj, along the semicircle from 0, 1 to 0, negative 1, where x is positive. So this is sort of the right side of your unit circle. Remember, when you're thinking about a line integral, it's how does the vector field go along this path? So I'm really interested in what does this vector field look like along the path. If I get lucky, my path can be broken down to just dx or dy, and my vector field might be constant along the path, like in some of our 18.1 problems. That's not going to be the case here because I got the circle. Sometimes I can tell that the vector field and my path are perpendicular all along the path, and then it becomes obvious, so to speak, that it's 0. Or I might get a vector field that's constant along my path, which in this case it actually is, because the magnitude of this vector field is the square root of x squared plus y squared, and my path is x squared plus y squared equals 1. So the magnitude of all these vectors along my path is always 1, but they will not be tangent. So I'm going to have to actually work it out. I can see that here's a picture of the vector field. Whoops, and this is not what I wanted to do. This is a vector field that we've seen in other problems. We're familiar with it, hopefully. It looks like the hyperbolas. So I can see, let me erase the Scrabble here. I can see that this has, basically the hyperbolic shape kind of scrolling, here when I come in, going towards the origin and then away from the origin, right? As I move from left to right. And here as I move from down to up towards the origin, away from the origin. So if I look here from 0, 1, here's the top of my path, and I end at 0, negative 1 down here, and I want to go on the right half of my unit circle. Here's my path C, and I'm going in this direction, right, from the top down to the bottom. And my goal here is to find the line integral of this vector field along this path. So I'm going to have to actually do it the long way, but what I do notice is that when I'm going in this way up at the top, they seem to be with my path. Then here, some of them are going to be tangent going in the opposite direction. And then down here, they seem to have the same pattern, but going in the opposite direction. So I would guess that my line integral will be 0 because the first top, the quarter of this first little quarter circle, this arc here, is going to be have a line integral that is the same value, but opposite sign is down below. Because I can see all the vectors are the same magnitude, and then they switch directions down here on my path. So let's actually do the work to work that out. Again, you can always just jump in and do the computation, but I do think the pictures help us. So my first step would be to parameterize my path. So here my path is a circle, and it's going to be going, in this case, counterclockwise, right? But clockwise, starting up at the top. So I actually want the x to be sine. So I'm going to have sine of t is my I component. That's x of t in parameterization. And cosine of t would be my j component, right? That would be y of t if I wanted to write it as parametric curves. Because I want clockwise starting at 0, 1. I actually only want where x is positive the first half of the circle. So I'm going to end here when t gets to pi. There's usually more than one way to parameterize the curve. As long as your curve is in fact the correct curve with the correct orientation, it starts and ends at the right place and follows the same path. How you parameterize it does not matter. You'll still get the same answer as long as your parameterization describes the same curve. I think this is the most straightforward way to do a circle that's clockwise starting at 0, 1. And I only want the half, so t is going to go from 0 to pi. Now to finish my problem, my line integral is actually f dot dr, so dr being r prime of t, so I'm going to take the derivative here. So when I take the derivative, I'm going to get the cosine of ti minus the sine of tj. And then when I plug in, I'll write that up here. I want to rewrite my vector field also in terms of t. So that's our notation. I'm plugging in my vector valued function into my vector field. This means instead of y, I'm using cosine of t. And instead of x, I would replace that with sine of t. So here we're going to get cosine of t j plus cosine of t I plus sine of t j. for my vector field. Now I can take the dot product of my vector field and each piece of my path, right? R prime t dt is like my dr. So when I take this dot product, I'm going to get cosine squared. It looks like I should get cosine squared minus sine squared. Let me just move this next thing here out of our way so I have room to work. Move this product. All right. So when I take the dot product, I'm going to get that integral. I'm doing the integral from 0 to pi because that's my bounds of t. Here we're going to get the cosine squared of t minus the sine squared of t dt. And now this is a single variable function. Here I would recommend that you use a trig identity or some of your other clever tools. If you look at this carefully, this is actually the cosine of 2t. So I would do it in that way, by using a trig identity. You could also break it up and do the integral of cosine squared and sine squared and use the table, use by parts, all kinds of clever ways. I think doing a trig identity to simplify here is going to make my life the easiest. And then I can ultimately do a u sub to get rid of that 2t. And when I do the u sub and compute the integral, we get 0 as we expected. I would take some time to finish doing that integration. Make sure you do remember how to do some basic trig integration and that you can get that, but that makes sense from our picture. So again, the steps were to parameterize the curve, find the derivative of that vector valued function that describes our curve, find the vector field that was given to me in terms of x and y, write that in terms of t, and then find the dot product of the vector field and r prime. Right, my line integral is the integral of the vector field dot dr, where dr is the derivative of this parameterized path, right? So here's r as my parameterized path, so dr, that differential, is my r prime dt. So now let's do another one. Another thing that came up that we didn't talk about as much in lecture, so I thought I would add an example, is an alternative notation. Ultimately, this is doing the same thing. I tend to prefer the notation of the r prime dt. I find it easier, but there is an alternative notation where I think of dr, instead of being r prime dt, I can rewrite dr in terms of my differentials dx, dy, dz. Right? Remember, r, my path, is x of ti, y of tj. We've mostly done the two components. We could also have a third component. So when I take the derivative, I take the derivative of each component. So now instead of dr, I replace that with dx, dy, dz, and I'm doing a dot product. So I would take the I component of my vector field times whatever the derivative is with respect to x, plus the j component with respect times dy, plus the z component times dz. Now, of course, I get an integral. It's going to be a little bit more complicated, or takes a little bit more work, I think, because I have to integrate with respect to x, with respect to y, and with respect to z. So that's why I prefer the other way, but it's ultimately the same. In this problem, for example, they just wanted you to practice with the actual setup. So there's nothing to integrate because they haven't told us the path. They're just saying, what would this look like if you were to write that? Well, if I were to write this out, my path would be given by some parameterization x of ti plus y of tj, right? That's how we always write our path. That's my position vector. I have not given the path, so I don't know exactly what the functions are for x and y. But the idea here is instead of taking r prime with respect to t, I can rewrite dr as the derivative of x is now my I component, and dy would be my j component, right? I only have a 2-component vector field, so I'm only looking at a 2-component path. So now when I want to do my line integral, which is the vector field dot dr, I don't have to change my vector field to be in terms of t because I'm keeping everything in terms of x and y. So when I do this dot product, I'm going to get 3x times dx plus negative y sine of x times dy. So I would be integrating. My bounds would have to be whatever the appropriate bounds for x and y would be along the path. And then that dot product would give me 3x dx minus y sine of x dy. And without knowing the path, I don't know exactly what dx and dy are or what the bounds are of integration. So I'm going to stop here, right? The point was to just set up this problem. And let's look at one last problem. where we actually use this notation to compute something. So in number 29, they're already telling us to set up this line integral. So ultimately, if you look carefully here, if we deconstruct this for a second, so you can kind of see where this came from, this looks like some vector field that was yi plus xj, right? That's our hyperbolic vector field that we've seen before. And they've given us the path, right? So, I have some path r of t. That's a vector valued function. So some function x of ti plus y of tj. But now I'm going to use this notation where my dr is dxi plus dyj. But now I know exactly what my x and y's are. So I can compute dx and dy. Ultimately, I'm still going to end up doing an integral with respect to t. I'm just sort of getting there in a different way by looking at this differential dr more in terms of a differential of x and y instead of putting it all in terms of t in the first place. So here we have y times dx, x times dy. So now I can just compute things and substitute it, right? So they're giving me x, so I can find dx. dx would be 2t dt. And they gave me what y is, so dy would be 3t squared dt. So now when I substitute everything in, right, they asked me to find the line integral along this path of y dx plus x dy. So I'm going to substitute. So I'm integrating when t goes from 1 to 5, because that was given. And instead, that's supposed to be a 5 there. And instead of y, I'm going to write t cubed. And now instead of dx, we have 2t dt. And then instead of x, I'm going to substitute t squared. And now instead of dy, we have 3t squared dt. So notice again, I've written this as an integral just with respect to t. I can, of course, look at this as, two separate integrals, or I could factor out, my dt and combine like terms. And it looks to me like I have 2t to the fourth plus 3t to the fourth. So that should be, right, I'm still going from 1 to 5. And I have 5 times t to the fourth dt when I combine everything. So that's ultimately just going to be t to the fifth. And the 5 should cancel out between 1 and 5. So that should be 5 to the fifth minus 1, which I get is 3,124. Again, the approach to the problem and how you parameterize the curve shouldn't matter. The line integral is going to be one number that represents if the field is with your path. So what I would challenge you to do on your own to check that this is just a difference in notation is to redo this problem right here, where you're given your vector field yi plus xt, and you're given the parameterizations, and do it in our other way, where now you write r prime of t and find the dot product of f in terms of t and verify for yourself that it in fact comes out the same way. So this differential notation is just another way to compute that dot product so that ultimately you can rewrite your line integral, which looks either like an integral with two variables or looks like an integral with vectors, to look like just a simple integral with one real valued variable. That's our ultimate goal, to be able to rewrite that dot product in the line integral to be just a single variable integral in terms of t. Whichever approach you use to get there should give you the same answer. So the rest of the homework in 18.2 should look very similar to the examples that we did today in our 30-minute example session of lecture, and like these 3 examples as well.